Okay, so for part 1 of homework 8-1 here, let's get going with multiple choice. So the first one, the position x of an object varies with the function of time here, for which of the following equations relating x to t is the motion of the object in simple harmonic motion. There are multiple correct answers here. And really, simple harmonic motion is going to be any type of sinusoidal curve. So any of these functions that follow a sine or a cosine function will model simple harmonic motion. Alright, so actually if I look through my options, there are 3 of these that will work. The option B here, where it's x equals 8 times cosine of 3t. The number out front simply represents the amplitude, so that doesn't affect the curve of the graph, right? And then the 3t, that just affects how wide the graph is, what the period is, but again, that doesn't affect the overall shape. Right, so that one works, as does option D, which is a sine curve, which still follows that simple harmonic pattern. And then finally option E as well. All that -1 does is it shifts the graph off a little bit right from its starting position, but it doesn't actually change the curve of the graph. So the only 2 here that don't work are sine squared, and that's because by squaring the sine function, that does change the curve. And then option C, which is a tangent, which we know that the tangent graphs look something more like that, and so that definitely does not work for our tangent function there. So B, D, and E are all appropriate for simple harmonic motion. Question 2 here just asks us to kind of analyze the aspects of motion for a spring system. And again, there are multiple correct choices here, so as we go through, we do have to consider each one. So the acceleration is maximum when the displacement is maximum. That is true, so that option is correct. Again, the bigger the maximum, or the bigger the displacement, excuse me, the higher the force and the higher the acceleration, so that is true. Option B, the acceleration is a maximum when the speed of the object is a maximum. That one is false. We know that the acceleration is at a maximum at the maximum compression or stretching, and the speed at those locations would be 0. So that one's false. The acceleration is maximum when the displacement of the object is 0. That one is also false. That just contradicts option A, so we know that one can't be true. D, the acceleration is 0 when the speed of the object is a maximum. That is also true. Right, the acceleration is 0 in the equilibrium position, and that's when the object reaches its highest speed as it's passing through the equilibrium position. So again, that one is true. And then E, the acceleration is a maximum when the object is initially at rest. And once again, that kind of goes right along with option A. The maximum acceleration happens at the amplitude, which there is a moment there. There's an instantaneous moment where the object is at rest at those positions. So A, D, and E for this question are the correct choices here. Question 3 here is a good one for us, kind of breaking down the important elements of the function, right, for these graphs. So they give us this cosine or sine curve, and then they ask us which of the following functions could represent that equation. So if I look through here, notice first and foremost, the first thing I look at is the amplitude. The amplitude is only 4 centimeters, and so that tells me right now it can't be option E, right? Option E shows that the amplitude would be 8 meters. And actually, these all should have said centimeters, by the way, or this should have been meters. The units there aren't consistent. So let's pretend these are all centimeters and not meters. But anyway, option E is definitely not right with that being 8 meters. So then I have to look at my other choices and see kind of which one makes the most sense. Well, if you look at the interior function, then everything else for options A, B, C, and D are identical, right? You've got the 2 pi over 8, and the 8 is simply representing the period. So that makes sense. It takes about 8 seconds for it to repeat the cycle. So again, that's consistent. So all of those options are the same there. The only difference is that phase constant, right? That phase shift in terms of what's happened to my functions. So we need to consider, right? Well, if this was a sine function, sine at a time of 0 would normally start at 0, right? So the sine of 0, well, the sine of 0 is normally 0, so that would be telling me it's be starting somewhere down there, right? So shifting it off by pi to the third would shift it, if we think about kind of our position in our unit circle here, shifting it off by pi to the third would start that sine function up here, which would start at about 1/2 of its amplitude, right? If that's 60 degrees, if it's pi over 30, the sine value of that, excuse me, not 1/2, would be radical 3 over 2, right? So that would be where that function is starting. So that's something to consider. And then the rest of these functions are cosine functions. Well, if I look through here, all of these shifts are less than half of the pi, right? Which means from our starting position, it would only shift it less than halfway through that rotation. So the correct answer on this one actually ends up being D, because if you look at that negative pi over 3 tells us we start a little bit behind, right? We start a little bit behind, and in fact it's 1/2 when we do cosine of pi over third, right? So if I do a new unit circle for that, I've got my starting position over here. Pi over 3 would be 60 degrees, so negative pi over 3 would be down here, 60 degrees, and the cosine value at that point is 1/2, right, instead of 1. So half of the amplitude would be 2 instead of 4. And so that's why it ends up being option D is the best choice, is because we're actually starting behind the motion for cosine, and we're starting at half of the amplitude instead of the full amplitude. So again, breaking down, I know it's kind of tricky to break through sine, cosine, and all those different functions. If you do have any further questions with this one, let me know. But a very good one for you guys to spend some time thinking about, making sure you're pretty comfortable interpreting this situation. Question 4 is then kind of the inverse, right? It's kind of the opposite question of question 3. This time they give us the amplitude and they give us the angular frequency, and we do have to be careful with that. But they give us those two measurements, and then they ask us which graph is representative of that. Well, first and foremost, the amplitude probably the easiest one to identify, right? If I look at the amplitude being 2 centimeters, that actually helps me rule out option D and option E immediately, because the amplitude of those graphs is only 1 centimeter, and so I know it can't be either one of those. So then it comes down to A, B, or C, right? So the angular frequency, and here's where we have to be careful. The angular frequency is not your frequency. It is not F, right? The angular frequency, and notice the units there, radians per second, that's actually our omega. So they're giving us the omega, they're giving us the angular velocity, if you will, in radians per second. Can we use that to help us find the angular frequency, or excuse me, the regular frequency? And the answer to that's yes. We know 2 pi times the frequency equals my angular frequency. So then all I have to do is take that measurement and divide it by 2 pi. Right? So take my 2 radians per second and divide it by 2 pi radians, and that's going to give me cycles per second, which is my actual frequency. Right? So obviously here you could just simplify this, or you could round it off, but we end up getting 1 over pi, which if this is the frequency, if that's the frequency, that means my period would be pi over 1, right, or pi. So then looking at these graphs, we want to identify which one has a period of about 3.14. Well, again, if I look through here, option C definitely takes longer than 3.14 seconds before it even, right, it takes about 3 seconds to even reach equilibrium, so that's not right. Option A, we look here, it goes from a crest down to a trough and then back up to a crest in about 2 seconds, maybe even a little bit less than that, which again would not be consistent with a period of 3.14. Option B starts at a crest, goes down through a trough, and back up to a crest right around 3 seconds, maybe just barely after 3 seconds, which would be consistent with my 3.14 for the period. So option B is the correct option for the 4th multiple choice question. Okay, so again, questions 3 and 4, very good ones to make sure you're comfortable interpreting, making sure you're comfortable breaking up those graphs and figuring them out from there. Question 5 here is a good concept question. It's one that they love to take advantage of. The period for an oscillating spring system is 2 pi times the square root of m over k. And if I look at that, they say, so what happens to the period if the amplitude is doubled, right? If it goes from A to 2A. And the reason this question is so loved and the reason it's so tricky is because it doesn't make any impact on the spring system, right? So the period does not depend on the amplitude at all. Right, now this is again assuming that we are working with a small amplitude, which we will always assume unless they tell us otherwise. But if I compress it A and then I compress it 2A, the period, the amount of time that it takes for one cycle, is the same for either of those situations. So again, the amplitude does not affect the period for any small amplitude of displacement. Okay, so question 6 is a good one for getting us comfortable finding our maximum speed and our maximum acceleration. Part A says, what's the maximum speed of this situation here? Well, they give me the amplitude of 0.012 meters, and then they give me the frequency here. They ask us to find the maximum speed. Again, the easiest way to find the maximum speed, I know we could try and use a formula, try and use an equation. The easiest way to do it, though, is to come down to this, right? The maximum speed happens, again, if we model this using uniform circular motion. The maximum speed happens when we have 2 pi times the amplitude divided by the period. Well, they didn't give me the period, so I could either use the frequency to find the period, or the other option is, if I think of this equation as 2 pi amplitude times 1 over the period, then isn't this really 2 pi the amplitude times the frequency? right? So the maximum velocity equals 2 pi times my amplitude of 0.0127 times my frequency of 2.55 hertz. Right, and so at this point it's just a matter of calculating that number and seeing what we get. And we should get about 0.2034. And obviously you can round that off more so than I did, but that's what I get for my maximum velocity for this system. Okay, so got that part taken care of. And probably that was the easier of the two parts for most of us. So then what about the maximum acceleration? How are we going to find that? Well, there's actually a couple different ways you could go about doing this. There's a couple different routes you could take. You could do the fact that the period equals 2 pi times the square root of m over k, and then you could solve for these two variables together and use that in combination with the maximum force equals k times x and go from there. You definitely can use this as well. The other shortcut that I would like you guys to start to get comfortable with, though, is the maximum acceleration. And if you look at the derivatives that we found for the velocity and acceleration function, you can see this. But the maximum acceleration equals the opposite of the amplitude times the angular frequency or the angular velocity squared. Right? And the angular frequency or the angular velocity would be 2 pi times the frequency. Right? So I can find that number easy enough, and then I can just plug that in and square that. So again, the maximum acceleration equals negative, and then again the amplitude of 0.0127 times that quantity squared. So calculating this, and by the way, that 16.02 just comes from plugging the frequency in. So that's all I did for that. But finding that maximum acceleration should be about negative 3.26. You could drop the negative, right? It's going to be a maximum at a positive and a negative at some point too. Okay, so I'll go ahead and leave the negative in there, but obviously positive 3.26 is also perfectly acceptable. So I would recommend that we start to get comfortable using this, and again, that just comes from the second derivative of our position function. That's where that equation comes from here. But you can also use the period and the force to help you work it out, and you should find about the same answer depending on some rounding. So anyway, hopefully this question's not too bad, but a very big one for us to look through. Okay, so question 7 is a very good one to make sure you're getting comfortable with here, as it starts to break up the phase constant, as we're not starting at the normal position, right? So the general equation that I'm looking at here is something like this, right? I know my position as a function of displacement, or as my displacement as a function of time, I should say. Amplitude times cosine times whichever piece I'm choosing this to be, plus that phase constant. And as I read through this question, they tell me at time of 0 the object starts at 0 meters, which means if I'm using the cosine function, I've got to make sure I'm adding phase constant. And so the first thing we want to think about is, what would that phase constant be? Well, here's my circle, right? Normally, cosine would be starting over here at 0, but again, it's telling us instead it's starting at a horizontal position of 0, which would mean it's starting either at this location up here or this location down here. Now, you could technically choose either one of those and it would be fine. It would be fine either way. I will go ahead and choose the top position here to be where we're starting at. So in terms of radians, that is pi over 2, right? That's where cosine first equals 0 is at pi over 2. So then that tells me, as I'm plugging in my values, I know the amplitude is 0.12. I've got my cosine. Because they gave me the frequency, I'm actually going to use, instead of omega, I'm going to use 2 pi f t instead, right? So 2 pi times the frequency, which is, what do we got, 9.7, and then t, and then plus my phase constant of pi over 2. And then at this point, it really is just a matter of solving. They tell me when is it at 0.048, so I plug in 0.048 over there, and I just solve this equation for the value that I need, right? So solving this out here, I end up getting 0.4 when I divide both sides by 0.12 equals cosine of 2 pi 9.7 t plus pi over 2. And then inverse cosine, right, as I do the inverse cosine of both sides, I get 1.16. When I do the inverse cosine of 0.4, I get 1.16, and then 2 pi 9.7 t, and then plus pi over 2. At this point, it's just algebra. Subtract the pi over 2 over, and then divide by this whole mess. We get t equals negative 0.0068, and in fact it would be positive in the other direction as well. So our correct answer here is a positive 0.0068 seconds from where it started. And the reason for that is, if it took negative seconds to go back this direction, it's going to take positive seconds to go that direction. So 0.0068 seconds is our final answer for this one. Again, a good question to look through, so let me know if you have questions on it.